Okay, this is 12B. This is talking about components of vector quantities in given directions. So if we have a look back at 12A, they're talking about, here they're saying, let's have a look. They're saying, well, what is the total vertical force that this experiences if you're adding these two forces together? And that's obviously really easy. You put 5 and minus 2 together to give you 3. But it could say how much of this vector A is acting in the direction of B, maybe. Sorry if I call that one lowercase a and this one lowercase b. And I say how much of this is acting in this direction. And that's what we're coming up to next. We're saying, well, instead of just splitting it into horizontal or vertical, we're asking how much of a vector is applying in a particular other vector's direction. Okay, so there's a little investigation for this one, which you can obviously do yourself. But I'm going to do it now as well, and you can perhaps go through it at the same time too. But maybe you could try and do it first. So let's see, it says let A be an angle between two non-parallel vectors A and B. So let's just set these two things up. Set this up, and still playing up a little bit. Okay, so there's just an XY grid here, Cartesian grid. And let me say, I don't know, here's A, and I don't know, here's B. Okay, so there's my vector A, and there's my vector B. So, and there's an angle between them of theta. It says, show that the component of A in the direction of B can be written as A cos theta. So what they mean is, if I take that back down here, that's meant to be sort of a right angle triangle that I'm creating there. And what we're looking for is this length here. That's the amount of A which is acting in the direction of B. In fact, this other measurement here, that's the amount of A which is acting, the component of A which is acting perpendicular to B. But in this case, they're asking us for the green line here. Okay, so show that the component of A in the direction of B can be written in this form, A cos theta. So that's just really simple trigonometry, in fact. So we're just saying here, look, there's a right angle triangle. We want to know the length of the adjacent here when we're given the hypotenuse. So that must be cos. And so the adjacent is equal to, it's going to be the length of A, which is the magnitude of A, multiplied by cos of the angle between the two vectors. Oh, and there we go, we're done. So it was just a diagram and cos there and a right angle triangle that was needed. Okay, so that's done. Where A is the magnitude of A, yeah, that's done. Okay, now question 2, it says find a similar expression for the component of A perpendicular to B. Now, if we were going to set that one up, similar, let's just do the same two vectors. We've got A, and you can imagine what the formula is going to be here. And there's B. Now, in the direction of A continues off in this direction here. There's still your theta in between them. But now we're going to make the right angle triangle by going this way around. Okay, so we're now looking for this green length. Again, that's a reason why we're going to use cosine again, and we're still going to get the length of B through cos of the angle. Okay, so that's just applying SOHCAHTOA or trigonometry again in a right angle triangle in that case. I just had to extend this line a little bit here just to show where that right angle triangle was. I had to extend this vector because it was quite short. Okay, so that's part 2 done. Now part 3, it says rewrite the expression for the component of A in the direction of B in terms of the scalar product of A and B. Now, remember the scalar product? We had A dot B is equal to the magnitude of A by the magnitude of B because of the angle in between. So if we rearrange that, we'll get magnitude of A cos theta is equal to A dot B divided by the magnitude of B. All I've done is taken this to this side and I've written it the other way around. So there we go, that's our expression. And in a similar way, this one over here is going to be dot B over the magnitude of A. So let's just recap that because you'll need to know that. It's saying that the expression for the component of A in the direction of B is the dot product, but then divided by the size of B. Okay, because the size of B is not important, it's just the direction of B here. So we find a unit vector for B really. In that case, by dividing by B, making B the size of 1 instead of the size of the magnitude of B. Okay, so that's why we're dividing by the magnitude of B. Okay, so we've done those ones there, all good. All right, now let's look at the next part of this. So the next part says, hence find the components of. Let's just have a little look. So we're going to use those formulas. It says, hence find the components of 1, 2, 3 in the direction of this thing here. Now we just need to set this one up as RA and this one up as RB, and then we can do A dot B divided by the magnitude of B. Now magnitude of B I can see is 3 squared plus 4 squared minus 3 all squared rather. I can see that's the 3, 4, 5 triangle, so that's going to have a magnitude of 5. And A dot B, remember how to do that one? It's 1 times minus 3 plus 4 times 2 plus 0 times 1, which is going to be 0. Put it on the end. And that gives us 8, and take away 3 is 5. So we get 5 there, 5, which is 1. So the amount of this, which is acting in the direction of this, is just of size 1. Okay, and you can do similar to this one here as